Hi everyone, in this lecture I'm going to continue the subject of predicates and quantifiers by showing you different examples. And then in the following sections I will talk about different types of quantified statements and how we can negate them using an extension of De Morgan's law. Basically, if we show the truth value of a statement using a function like p of a variable like x, then for example, if you write p of x as a truth value of a statement, that p of x would be a symbol for a predicate, because predicate is a logical statement whose truth value is a function of one or more variables. If p of x is defined to be the statement, for example, x is an odd number, then p of 5 corresponds to the statement 5 is an odd number. So we replace x by 5. And p of 5 is a proposition because it has a well-defined truth value. In fact, p of 5 is true. Also, you can see some other examples of predicates like q of x and y and r of x, y, and z with more than one variables. So q of x and y has two variables. That's why we write two x and y. I mean, we write two variables like x and y inside parentheses. They are separated by comma. And this is how we define it. For example, q of x and y is this equality. X squared is equal to y, which means that if x squared is equal to y, then q of x and y would be true. Otherwise, q of x and y would be false. Same for r of x, y, and z. We have three variables separated by comma inside parentheses. And then the meaning of r of x, y, and z is x plus y is equal to z, which means if x plus y is equal to z, then r of x, y, and z would be true. Otherwise, r of x, y, and z would be false. As a result, you can say that the proposition q of 5 and 25 is true because 5 squared is equal to 25. But the proposition 2, 3, and 6 is false because 2 plus 3 is not equal to 6. In the first example, q of 5 and 25, x is 5 and y is 25. Therefore, x squared is equal to y. In the second example, x is equal to 2 and y is equal to 3. Therefore, x plus y is equal to 5, which is not equal to the value that z is replaced by, which is 6. Therefore, r of 2, 3, and 6 is false. The statement every x p of x is called a universally quantified statement. In fact, the symbol upside down a is read for every or for all, and it shows a universal quantifier. And then for every x p of x is a proposition. Why? Because it's either true or false. For every x p of x is true if and only if p of n is true for every n in the as we said before, every variable participating in a predicate must be part of a set called domain. So x can be replaced by only the values inside the domain of x. So when we say for every x p of x, this is true if and only if p of n is true for every n in the domain of x. If the domain is a finite set of elements like a1, a2, all the way to ak, then you can write the following equivalence. You can replace or you can interchangeably use the conjunction of k elements p of a1, p of a2, all the way to p of ak, instead of the universally quantified statement for every x p of x. What does it mean? It means that instead of saying for every x in the domain p of x is true, we basically write down the predicate for every element of the domain, and then we find the conjunction of all of those statements. They both are logically equivalent. So, I mean, that's the way that we define a universally quantified statement. Now, let's take a look at an example in algebra. For example, we want to prove that for every x uh, in the domain of positive real numbers, 1 over x plus 1 is less than 1. How can we prove it? We have to first start with the assumption that we said x is a positive real number, therefore x is greater than 0. Every x in the domain should be greater than 0, right? Because the domain is positive real numbers. And then you can add 1 to both sides of the inequality. Therefore, 1 would be less than x plus 1. And then obviously you can divide both sides by a positive number, and you can still have the same inequality with the same direction because we divide both sides by a positive number. The positive number that we divide both sides is x plus 1. X was positive, so x plus 1 is also positive because a positive number like x plus another positive 1 would result in another positive number. Anyways, so when you divide both sides of the inequality by in the left hand side, you get 1 over x plus 1, and in the right hand side, you get x plus 1 over x plus 1, which is equal to 1. And then you get the green, inequality that you see at the end, which is what we were going to prove. So the proof is complete, and we prove that for any positive integer x, the inequality is true. Therefore, the universally quantified statements that, mentioned at the beginning is true. If you remember, we defined a counterexample for a universally quantified statement, and we said the counterexample is the value in the domain of the variable of the predicate that makes the predicate false for the universally quantified statement. So if you have a statement like this, for every x squared is greater than x, then and then you know that the domain of x is the set of all positive integers, then you can find a value in the set of all positive integers that if you replace x by it, then x squared would not be greater than x. What's the example? To find the example, all you need to do is set x equal to 1. So if you set x equal to 1, then x squared would be 1 squared, which is 1, and it is equal to x. Therefore, the statement x squared is greater than x is not true because x squared and x are not uh, are equal, in fact. So x squared is not greater than x. Therefore, x is equal to 1 is a counterexample of the universally quantified statement that we saw, and it shows that the statement for every x squared is greater than x is false. So in fact, if you want to disprove a universally quantified statement, you don't need to do anything but to find a counterexample for that universally quantified statement. So you need to show that there is a value in the domain of the variable that makes the predicate false. Also, we showed that the statement there exists an x is called an existentially quantified statement. The symbol backward of capital letter E, is read as there exists or there is. And when you put a quantifier there exists before if a variable, and after that you mention predicate, then the whole statement is called an existentially quantified statement. So this statement, there exists an x p of x, is a proposition because it's either true or false, and it is true if and only if true for at least one value n in the domain of variable x. So it means that if you find a value in the domain of variable x that makes p of x true, then the existentially quantified statement is true. Otherwise, it is false. So if we assume that the domain of variable x is a finite set of elements like a1, a2, all the way to ak, then you can write the following logical equivalence. You can say there exists an x p of x is logically equivalent to the disjunction of these statements: p of a1, p of a2, p of a3, all the way to p of ak, which means that we can replace x by all the elements in the finite set of elements a1 all the way to ak, which was the domain of variable x, and then the k obtained statements should be ORed together in order to construct the existentially quantified statement, which means that p of x true, there exists x p of x is true if and only if p of a1 is true, or p of a2 is true, or p of a3 is true all the way, or p of ak is true. So that's the definition of how, that's the definition of an existential statement. How and when we can say an existentially quantified statement is true. In order to show that, for example, this existentially quantified statement that exists an x, x plus 1 is less than x is false, what we can do is assume that that inequality is true, and then try to conclude and reach to a inequality that is impossible to be true. So, for example, if x plus 1 is less than x is true, you can subtract both sides. You can subtract x from both sides of the inequality, and you get one from the you can get 1 in the left hand side and 0 in the right hand side. So if you have x plus 1 is less than x, if you subtract x from the left hand side, you get x plus 1 minus x, which is 1, and in the right hand side you have x minus x, which is 0. So this inequality doesn't hold regardless of the value of x. So for no value of x, the inequality x plus 1 less than x is true. Therefore, the existential statement there exists an x such that x plus 1 is less than x is false, because for no value in the domain, the inequality x plus 1 less than x is true. In this slide, I'm going to define a number of terminologies that we will use later. The universal and existential quantifiers that we have seen so far are generically called quantifiers. And a logical statement that includes a universal or existential quantifier is called a quantified statement. And a variable x in the predicate p of x is called a free variable because the variable is free to take any value in the domain. However, in the opposite of free variable, we have bound variable. The variable x in the statement for every x p of x is a bound variable because the variable is bound to a quantifier. So if the variable of a predicate is bound to a quantifier, then that variable is called the bound variable. But if it is not, then it is called a free variable. Let's see the following example and see whether a quantified statement about an integer is true or false. Let's assume that P and Q represent the following predicates. P of X, represents X is prime, and Q of X is the symbol for the sentence X is a perfect square, which means that X can be written in the form of y squared, where y is an integer. And then let's assume that the domain of X in both predicates is the set of all positive integers. Is indicate whether each logical expression in the following four cases is a proposition, and if so, then give its truth value. The first part is there exists an X Q of X. So this case, the first part, is a proposition in Q of X that is bound to an existential statement. And it basically means that there exists a number, a positive integer, that is a perfect square. And obviously, this is true because, for example, square 4 is a perfect square, 9 is a perfect square. So you can find a value in the set of all positive integers, which is the domain of X, that makes Q of X true. Therefore, it's a true proposition. Part B says for every X, Q of X and not P of X. Notice here that the conjunction that you see in this in part B is a conjunction between the whole quantified statement in the left and not P of X in the right. So you have to always remember that the priority of universally quantified statement, the priority of a universal quantifier is always higher than other logical operations like conjunction or disjunction or negation. Therefore, when we write for every x q of x and not p of x, that would be a conjunction of a universally quantified statement in the left and a negation of p of x in the right. Therefore, it's not a proposition because the variable x in p of x in the right-hand side operand of conjunction is not bound by any quantifier. Therefore, it's not a proposition and you cannot specify the truth value of this statement. Basically, the truth value of this statement would be dependent on the value of x. So we can't say anything about it. In part C, we have for every x q of x or p of 3. So in this case, the right hand side operand of this junction is p of 3, which is a proposition saying that 3 is prime. And obviously it is true. The left hand side operand of this junction for every x q of x, which says every positive integer is a perfect square. So we have a disjunction of two propositions. The left hand side proposition, which is a universally quantified statement, is false. The right hand side proposition is obviously true because 3 is a prime number. Therefore, the disjunction of both is true because false or true is true. In the last part, we have there exists an x, q of x, and p of x. Here, in this existentially quantified statement, we have a parenthesis over the conjunction of q of x and p of x. So it is there exists an x in parentheses a conjunction of q of x and p of x. Therefore, both x's in q and p are bound to the existential quantifier there exists an x. Therefore, there is no free variable, which means that we have a proposition. And if you think about the truth value of the proposition, it is false. Why? Because q of x and p of x, the conjunction of q and p means that x is both perfect square. And you cannot find any positive integer that is both a perfect square and a prime number. If you think about 1, 1 is not prime. 2, 2 is prime, but it's not perfect square. 3, 3 is prime, but it's not a perfect square. 4 is neither prime nor perfect square. We cannot continue checking all the positive integers. If you want to really prove that this proposition is false, you need a complete and general proof that we will talk about those kind of proofs later in the following chapters. Next, we're going to talk about how to negate a quantified statement using the extension of. So I'm sure that you remember the De Morgan's law. It is a law that specifies the best way or the appropriate way for distributing a negation over a disjunction or a negation over a conjunction. So you remember that if the domain of a variable was a set of finite elements, then the universal statement could be rewritten as the conjunction of a bunch of statements. So if we have the negation of for all x p of x, if you rewrite the universally quantified statements as the conjunction of p of a1, p of a2, all the way to p of an, where a1, a2, all the way to an is the domain of x, then the negation of this conjunction based on the De Morgan's law would be the disjunction of of each statement. So it would be not p of a1 or not p of a2 or not p of a3 all the way to not p of an. Now, if you remember, we said the disjunction of a number of elements can be replaced by an existential statement. So it would be an existentially quantified statement with the bound variable x, and then you can simply replace a1, a2 all the way to an by x. So you can say this whole disjunction is an existential statement. There exists an x such that negation of p of x or not p of x. Therefore, we come up with this negation. When you want to negate a universally quantified statement, do is to convert the universal quantifier to an existential quantifier and then negate the predicate inside the quantified statement. So p of x becomes not p of x, and for all symbol becomes there exists symbol. The same exact opposite case. When you have a negation of existential statement, you can say that it could be universal statement in the following way. The negation of there exists x p of x is logically equivalent to for every x not p of x. Again, for this logical equivalence, you can have the similar justification using the De Morgan's law. So let's see an example of how to apply the De Morgan's law for quantified statements. In this case, prove that the left-hand side the left-hand side existentially quantified statement equivalent to the right-hand side universally quantified statements. In order to prove this logical equivalence, what we do is we first apply the De Morgan's law by converting the existential statement to a universal statement and negate the predicate inside the existential statement. So it would be for every x, negation of not p of x or q of x and not r of x. And then we distribute the outermost negation over the parentheses, which is a disjunction. Again, based on De Morgan's law, when you distribute a negation over a disjunction, the disjunction becomes a conjunction, and therefore we have negation of p of x conjunction with negation of q of x and not r of x. Apply double negation to get rid of these two back-to-back negations before p of x. And then again, second operand of the conjunction, the outermost conjunction. As you see, it's a negation over a conjunction. Based on the De Morgan's law, you can distribute a negation over the conjunction by converting the conjunction to a disjunction and negating both operands of that conjunction. So the negation of q of x and not x becomes not q of x or not r of x. If you apply double negation law on not r of x, it becomes r of x, right? So the simplest form is the right-hand side expression in the logical equivalence that you see at the beginning of the slide, which is for every x, p of x and not q of x or r of x. In this slide, we're going to see an example of nested quantifiers. We can have a combination of universal quantifier and existential quantifier. A logical expression with more than one quantifier that bind different variables in the same predicate is said to have nested quantifiers. For example, for every x, there exists a y such that p of x and y. So in this case, both x and y are bound variables. X is bound by the universal quantifier, y is bound by an existential quantifier. And it is important to note that the universal quantifier comes before the existential quantifier. Remember, the order of quantifiers is very important and it matters and it can affect the truth value of the whole statement. The second example is for every x, p of x and y, right? So in this case, x is bound, but y is a free variable because there's no quantifier that can bind, y. And the last one is a combination of two existential quantifiers. There exists a y and there exists a z such that t of x, y, and z. Y and z are both bound, but x is free. So it is easy to see that the order of two existential quantifier doesn't matter. Instead of saying there exists a y, there exists a z, t of x, y, and z, you can say there exists a z and then there exists a y. You can just swap these two that exist symbols, and you still have the same statement. So in this example, y and z are bound to two existential quantifiers, but x is a free variable. So let's see an example of nested quantifiers and see how we can specify the truth value of a logical expression with different quantifiers. Let's assume that m of x and y is a predicate with two variables x and y, and then x and y, each one of them can be replaced by one of the numbers 1, 2, or 3. So the domain of x and y for both variables participating in the predicate m is the set including only three numbers, three integers, 1, 2, and 3. This table with 9 truth values can specify the truth value of predicate m for any combination of x and y values. So, for example, this is how you can read this table. M of 1 and 1, so the predicate m when x and y are both replaced by 1, has a true value. M of 1 and 2 has false value. M of 1 and 3 has true value. M of 2 and 1 has true value. M of 2 and 2 has false value. M of 2 and 3 has true value. M of 3 and 1 is true. 3 and 2 is true. Finally, M of 3 and 3 is false. So the question is indicate whether each of the logical expressions is a proposition. If so, indicate whether it is true or false. In first part, we have m of 1 and 1. True. I just told you how to read that table. Second part, for every y, m of x and y. This is not a proposition because x is not bound to any quantifier. So the value of this universal quantified statement is a variable of x. So you can't find the value of this universally quantified statement. Part C, there exists an x such that m of x and 3. What does it mean? It means that there is a value for x such that if y is 3, then m becomes true. And this is a proposition because you have only one variable that is bound to the existential statement. And the truth value of this proposition is true because in the last column, the column in which y is equal to 3, you can find at least one true values. At least, in fact, you can find two true values, right? One is in this row, in the first row, and the other one is in the second row. So for the value of x equal to 1 or x equal to 2, the statement m of x and 3 becomes true. So the existentially quantified statement is true. In part D, we have a nested quantified statement. We have there exists an x, there exists a y such that m of x and y, which means that there is a value for x and there is a value for y that makes m of x and y true. What does it mean? It means that at least one of these 9 values that you see in the whole table must be true. There is a combination of values for x and y that makes m of x and y true. This is obviously the case. You can you have uh, 6 entries that are true in this table, so any of them would be a good example. For example, x is 1, y is 3. X is 1, y is 1. X is 2, y is 1. X is 3, y is 1. They are all examples showing that this existential statement in part D is true. The last one is there exists an x such that for every y, m of x and y. So this is an example of a nested quantified statement. It's an existential universal statement. The first part is an existential quantifier. The second part is a universal quantifier. Let's see how we can translate this proposition. First of all, is it a proposition? The answer is yes. Why? Because there's no free variable. X is bound to an existential statement, y is bound to a universal statement or to a universal quantifier. I'm sorry. So x is bound to an existential quantifier, y is bound to a universal quantifier. Therefore, this statement is a proposition. It has a truth value. Is it true or is it false? Let's first understand the meaning of this statement. It says there exists an x such that for every y in the domain of 1, 2, and 3, m of x and y is true. What does it mean? It means that there is one row in this table that you see in the there is one row, one value for x, one row that has all true values, which means that for every y, no matter what the value of y is, that row has true values. Is it the case? The answer is no. The first row has one false value in the second column. The second row, again, it has one false value in the second column. The last row has also one false value in the last column. You see, true, true, false. If one of the rows was true, 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 then this proposition was true. But now it's not.